Ladies and gentlemen, welcome. We're going to try to do a speed review of lessons 2, 4, and 5 of this unit. Try and do a speed review so that my entire video will fit on my YouTube channel without me having to post two separate parts to it. See what I can do. Before I forget, subscribe to my channel. Make me millions. All right. The thing we're investigating in this unit is how a speaker can produce a sound. We started off with video like this. We notice that as the speaker is producing a sound, it's moving around. And we weren't sure if the sound caused the moving or the moving caused the sound. Not 100% sure about that. But we are trying to figure it out. So we started by simply dissecting a speaker. So we took this speaker apart. We noticed that it had like a paper funnel part on the inside, another piece of paper, copper coil of wire, magnet was all the way down in there. Those were all the important parts we thought. And then we actually built our own speaker. It was interesting. We didn't need near as many materials as what we thought. All we needed to build our own speaker was a plastic cup, some copper wire, and magnets. And when we hooked these wires up to our computer, just like we did our other speaker, then this produced a sound. Crazy. So we thought all we need to make to have a speaker produce a sound is then a funnel of some sort. It doesn't even have to be paper, like this plastic one worked. We do need some copper wire, and we need a magnet. We knew the magnet was important because when we took the magnet away, the sound stopped. When we put the magnet close to the cup or the copper wire, then the sound started again. And sometimes if we just moved it a little bit away, it got quieter. When we moved it closer, it got louder. Some people even tried more magnets, and that made the sound louder. So we knew magnets were somehow important. So we decided to investigate magnets a little bit more. See if we could then figure out how our speaker would work. We started by just playing with magnets. We saw they can attract other magnets without touching. They can repel. Whoa, that's still attracting. They can repel or push on other magnets without touching. They can attract things like a paper clip without touching, or a nail. We saw it also moved our compass needle without touching it. Okay, so that'll lead us to a few different conclusions. First, we said that magnets can pull and push other magnets without touching them. I got the beautiful little drawing over here. Next, we saw magnets could pull objects made of iron without touching them, because we saw that our paper clip had iron in it, our nail had iron in it, the compass needle, all the things that the magnet was pulling had iron in them. We also saw, which was very interesting, that the magnet didn't interact with our copper coil. So there was nothing going on between our magnet and our copper coil until we put electricity through it. So when I hooked it up to my battery, then there was a repelling force going on. There was attraction between the two. But again, only when I had electricity going through it. If I disconnect my battery, now no repelling, no attracting anymore. So we summarize all those things right there on our progress tracker. Again, with beautiful pictures. I drew those all by myself. Okay. That then led us to ask the question, well, how on earth can a magnet pull or push something without touching it? We investigated this a couple ways. First, with a million tiny little pieces of iron, and then with a compass. Not a million compasses. First just one, then like 6, and then we simulated a million. So let's start with what we saw with the pieces of iron. We sprinkled a million little pieces of iron over our magnet, and here's what we saw. This beautiful picture here. It led us to a couple observations. First, it looks like there's a lot more iron pieces at the poles than in the middle of the magnet. Conclusion, the poles must be stronger, like the force that the poles has, the pull that the poles have must be stronger than the middle of the magnet. Next, we notice in this area around the magnet, there's no iron filings or no iron shavings or pieces. Our conclusion, they must have gotten pulled right to the magnet. So the pull right around the magnet must be really strong. And as you get further away from the magnet, you see some of the pieces of iron kind of line up, but the pull there must not be as strong. And if you get really far away from the magnet, like way over here in the corner, those pieces of iron didn't seem to move at all. So there must be no pull there. So the closer you are to the magnet, the stronger the pull must be. And the further away you get, the weaker the pull. What we're kind of visualizing here is what we called a magnetic field. A magnetic field is just an area around the magnet or a space around the magnet that experiences a force or can put a force on things. Then we investigated it with a bunch of compasses. Oh, I'm kind of lost my way here. Hold on. Let me pause. All right, I'm back. Oh, I really got lost there. So we put some compasses by our magnet. And when I put one here, I notice that little red needle points to north. It really shouldn't. That one must be messed up. There you go. That little red needle points away from north. If I put one here, that little red needle points away from north. And this one points away from north. And this one points, well, that's the same one that's messed up. I gotta find more. This little red needle points away from north, or the white one points toward south. And I'll just keep adding more and more. And we see that there's a direction to this magnetic field. It causes the compasses to point in a certain direction. So over here, they're pointing away from north. Over here, they're pointing, oh, is that one? No. There we go. If you look at the little green triangle, it's pointing towards the south. And if I flip the magnet, watch this, this is going to blow your mind. So just try to keep track of which direction the needles are pointing, and watch what happens when I flip the magnet. All the needles switch the direction. So now, like, all these red needles are pointing towards south. Here they're pointing away from south. Okay? So what we learned from this is there's a direction to the magnetic field. Then we looked at a simulation, because sometimes we can't set up what we would actually want to set up. Like if I could, I would take 10 million needle compasses and put them all around here and look at what direction the needles were pointing. That's not real feasible for us. So we looked at a simulation where they did this for us. So here we have, imagine 10 million compasses all around this magnet, and it's showing what direction the needles are pointing. So if I put a compass here, the needle would be pointing to the right. If I put it here, it would be pointing to the right again, but maybe a little bit down. If I put it over here on the other side of the magnet, it'd be pointing towards south. So here's all the different directions that this magnetic field has. And when we look at this, we see it looks very similar to our iron filing picture, where there's like parts in the magnetic field that go straight out. We see there's parts in this magnetic field that go straight out from the ends. We see parts in the magnetic field where it's kind of curved, like above and below. And we see here parts that are kind of curved, above and below. All right? So through these investigations with the iron pieces, the compass, the simulation, a few things we came away with. One, that a magnet has a magnetic field. It can put a force on things. Two, the magnetic field is stronger near the ends of the magnets, near the poles. Three, the magnetic field is stronger when you're closer to the magnet. And four, that the forces in this magnetic field have a direction. That's what we saw with the compasses, that they point in a certain direction. So that means the forces in this magnetic field have a certain direction. And what's interesting is this didn't just happen with our magnet. It also happened with, ouch. This gets hot. It also happened with, don't ever leave your wire hooked up to your battery because it gets really hot. When we hooked our battery up to I'm afraid of this now, our wire, and we put this to the compass, even this produced a magnetic field. So let's see if I can show that here without hurting myself again. So here we have all of our compasses yet, and now I'm running electricity through this wire, and watch what happens to the compasses when I put this wire near the compass. Do you see that some of them have changed direction? Similar to when I had a magnet near it. And if I flip this around, the needles flip the direction that they're pointing. At least some of them are. So this must not be as strong as a magnetic field, but it still is affecting the compasses. So even this, when it's hooked up to a battery, produces a magnetic field. Ouch, can you see that? Yeah. In lesson 5, the question we were investigating was, how does the magnetic field change when we add another magnet? Again, we investigated it with our million iron pieces, and again, we investigated it with a compass and our simulation. First, with the iron pieces, we saw that this is how the iron pieces arrange themselves when we had a south pole of one magnet facing a north pole of another magnet. We noticed that the iron pieces pushed away from each other so that there was no pieces of iron in between them. When we put a compass in between them, we saw that the compass needle pointed either straight up and down, pretty close to straight up and down, depending on which magnet I have it closer to. Yeah, straight up and down. And when we looked at the simulation, we could see why that was the case. So in the simulation, we add 2 magnets, and we have similar poles. Let me flip this one. Oh, let's make it north and north, just like our magnets were. Similar poles facing each other. Take a look at their magnetic fields. This one is pointing to the left. This one is pointing to the right. They are pointing in opposite directions. Their magnetic fields are going against each other. So then it would make sense why our compass needle wouldn't point to the right or to the left. It would just point up or down. It would make sense why our iron filings would get pushed out of the way, because the magnetic fields are going against each other. Their forces are in opposite directions. So it's almost like it pushes all the iron pieces out of the way. And it would make sense why, when we have two magnets together with similar poles, it would make sense why they would repel each other, because their magnetic fields are going in opposite directions. They're pushing basically against each other. If we flip one of the magnets and have opposite poles, we know that they attract, and when we consider what's going on with their fields, it makes sense. Here is what the iron pieces looked like when we had a north pole and a south pole facing each other. The pieces of iron all filled in the middle between the two magnets. When we put a compass in between, the compass needle pointed between the two. If we add more compasses, the compass needles just keep lining up in the same direction. And that's basically what's happening to the magnetic field, which they show in the simulation. In the simulation, if I add two magnets and flip one of them, you can see the fields are now lined up. They're pointing in the same direction, which would explain why our magnets attract each other when their opposite poles are facing. Their fields are like basically going together. They're lining up. They're in the same direction. So those magnets get pulled together. Okay? So that led us to add the following to our progress tracker. When similar poles are facing each other, they repel. So North Pole and North Pole will repel because their magnetic fields are in opposite directions. When opposite poles are facing each other, like North Pole and South Pole, they attract because their magnetic fields are going in the same direction. And then we tried to illustrate that here. So all of these pieces we're now going to try to put together to explain why our speaker works the way that it does. See ya.